So hello everyone, my name is Peter. I'm working for Cisco. I'm going to talk about our experience in using Datomic from an application that's not written in Clojure, but it's written in Scala. So for some of us, Clojure was a foreign country. And how can you say that? Datomic is not a Clojure database. Datomic is a JVM database, if you will. But at some point, you come into contact with its roots in Clojure. And for a Scala team, that can be perceived as something foreign. But before we discuss this question, why this is foreign a bit further, let me show you first what we did and how we did it. So the problem domain, the problem space that we're talking about is sort of configuration management, but not in the traditional sense where you configure infrastructure, but on an application level, where we wanted to configure whole software as a service platforms from a new application. So from a database point of view, that's not a very write-intensive task, right? There's people, users, setting up configuration, maybe testing it, and then sending it to remote systems to configure them. The only other requirement we had is that the whole thing that we were building should be deployed in a sort of cloudy environment, and which is something you can do with Datomic. But I think that was not the only reason why we chose to do it. There are some other compelling reasons that seem to make it a good fit for this problem. For example, the property that it does no in-place updates, but sort of retains all the history of your data, which is useful if you do configuration management. You want to go back to what you had before. The fact that it has something called what you could call reified transactions, and I'm going to show you in a minute how we used it for auditing purposes. But more than anything else, I think what made it attractive to me is that it has this interesting hybrid nature where it combines some of the things we appreciate in traditional databases, which is, for example, having a schema or asset semantics if you need them, with some of the properties that sort of the newer NoSQL stores have, which in Datomic's case is that you can scale the reads horizontally. So the stack we used to build this thing looked like that. We are using a thing called the Play framework, which probably doesn't tell you very much if you're Clojure programmers, but it's sort of a very popular web and HTTP framework in Scala. We were using a lot of queues in between these different components to ship the configuration to its destination. And we're using a technology called Apache Artemis for that, formerly known as Hornet Queue, which happens to be also one of the underpinnings of Datomic. And we use Datomic in combination with Apache Cassandra. So assume a general familiarity with Datomic in this audience. So you have to choose a sort of storage service when you use Datomic, and Cassandra is one of the options. You can also choose React or Amazon Dynamo and others. But we already had Apache Cassandra deployment, so this seemed to be a natural choice. So if you would like to visualize the thing, you could draw boxes like these, right? So we have some sort of UI, a browser, users interacting with the application through a browser, which we are serving through our API server, which gets its data from at least 3 Cassandra nodes. That's how many you need when you use Datomic. That's the minimum. Presumably to mediate the different consistency sort of properties of a eventual consistent data store with Datomic's consistency guarantees. And then I think the interesting thing what Datomic does in order to achieve these sort of hybrid properties is that it breaks up the database into its components and has them as separate processes. So the Cassandra nodes are sort of the storage service. Then you have this thing called the transactor, which is the single writer who writes back into the storage from your application, the transaction data you send to them. And then the third part is if you zoom into your application process, there's a thing called the peer library, which does all the heavy lifting when it comes to running your queries based on cleverly cached index data. So you have to, of course, size your heap accordingly in your application. So with this sort of setup, we thought we would be well set up to sort of handle also future demands. So if this application would become tremendously successful, we thought we could just scale by adding more API servers, or maybe use the high availability option on the transactor. But how do you actually go about using Datomic from Scala? Well, the first thing is, as I said, Datomic is not a Clojure database. So it's a JVM database, so there is a Java API, and you can just use that with interop. There's similar good interop in Scala as there is good Java interop in Clojure. But of course, people start building libraries around these Java APIs because it's not very idiomatic usually to use a Java API from a Scala application. So there are two libraries that try to do that. One is called Datomisca, the other one is called Molecule. I mean, in theory, there's also a REST API, but I haven't really explored how viable that is to build anything on the top of that. And I want now to take a very quick look at each of these libraries, because I think it's quite instructive to see how they approach this problem of adapting Datomic to this other language. So this is, I hope this is readable, is an example that I've chosen from the Datomisca library. And I think I've chosen that because, in my mind, it exemplifies the philosophy behind this library quite good. Because even if you don't know anything about Scala, but you have written a Datomic data log query, you recognize this immediately. Because this is just a query right there. Now, you could say, if you know something about Scala, well, that's a bit lame, that's just a string, right? It's actually a bit more clever than that, because this query thing around it is actually a Scala macro that parses this query and returns a typed representation of it that at least tells you something about it, how many inputs and how many outputs it has. But keep that in mind that this is a Scala macro. I come back to that point later when we talk about problems. So I think the philosophy behind this library is to represent the ideas or features of Datomic as closely as possible in Scala without adding any conceptual overhead, just sort of wrapping typed representation about these sort of untyped data structures. And to take a quick look at the other library, Molecule, which is also very impressive in many ways, but what you immediately recognize is that you don't recognize Datomic here. So that there's a conceptual layer in between. They have chosen to build a, I don't know, maybe object-oriented builder pattern style DSL on top of it. And these two things that we just saw, this one and this one, is the same query, right? So we choose to use Datomisca also because I wasn't aware of Molecule when we started out with this project. But let's talk a little bit about what I call the happy path, things that worked really well, that translated nicely from Clojure or Java into Scala. And one thing is, of course, and that follows from this property of not doing in-place updates, of retaining all the history of your entities and of your attributes, is that you have the history of everything available for queries. And that is in itself very interesting. But what I sort of find remarkable in retrospect is that the simplicity and at the same time flexibility of the underlying data model sort of has a lot of potential that you're not aware of when you start out. So to illustrate that, so we didn't anticipate certain requirements that we had to implement when we modeled out our problem. And at some point, a new requirement came up that we had to implement sort of the typical corporate password policy. And one of the constraints of that password policy was that you were not allowed to reuse passwords you had used previously. So when we thought about how do we go about implementing this, we realized oh, hold on a second, we don't have to change anything in our data model because everything is there. We just need to write a query that, and I've translated that for your convenience to Clojure, that goes into the history of this attribute of the password hash for a particular user, pulls out all the historic values of that password hash, and compares it with what the user proposes to use as its next password to answer that question. Is this a valid new password? The other thing that follows from that is that you can sort of time travel. You can retrieve a immutable version value of your database from one instant in the past and work with that. And again, this is something that's on the sort of conceptual level of Datomic that translates nicely into any language you use with it, as long as the APIs allow you to retrieve it, I guess. So when we had this requirement, for example, to build an API that also gave you historic views on this data, that was trivial to add because it's already there. Now, you can also to some extent travel into the future with Datomic, and it's maybe not the future, but one of many possible futures, sort of the Star Trek kind of parallel universe future. Because what you can do is you can use an API called with, it takes a database value and some transaction data, and you can, in your application process, calculate a new sort of speculative version of that database, how it would look like if you were to transact that data. So you don't go to the transactor, who is the single writer, you do that in your application process. And we use this in, I think, two ways. One way was that when you have relationships between entities, let's say you have an entity B that requires an entity A to be present. And let's further assume that A has a unique constraint on an attribute. So what might happen is that when you try to actually transact that into the database, that this transaction might fail because there is already an entity similar to A with an attribute with that same value in the database. So you send all the data to the transactor and it comes back and says, well, that's not possible. What we did instead was that we used this speculative version of the database before actually doing the round trip to the transactor, and transacted or asserted entity A and caught this error early and didn't even bother to calculate B, which might be expensive, and didn't even bother to go to the transactor. Now, of course, there are some pitfalls with this approach, because this speculative version of the database is sort of a local view. But the point I'm trying to make here is that it's sort of, again, one of those concepts that you can use no matter where you come from, which language you use. And the other thing I mentioned earlier is that Datomic has this idea or this concept of reified transactions. So if you think back to a traditional relational database, transactions are essentially ephemeral, right? They exist only while you execute them. And what you then have in your database is a sediment of that transaction, but the transaction itself is gone. And in Datomic, the transaction goes into the database as just another entity. And that opens up possibilities for interesting applications, because you can now add attribute to these entities. Add attributes like audit information. This is what I think many people do, and what we did also, to record who triggered this transaction and maybe why and where did he come from and things like that. And here you see, I mean, this is Scala code, but here you see how the library we used is similar in how it treats this transaction data. It's just data structures, and these two plus signs, we're just concatenating the transaction data that the user wants to transact and our additional audit information, in a similar way as you would concatenate two Clojure lists or two maps of maps or something. So this is the same concepts, the same sort of, you work with data structures also in the Scala library that we used to interact with Datomic. So these are the things that I think worked really well and where we didn't experience any friction. But I think you might be interested in those cases where we had to put in a bit more effort, where there was more work to be done. And one of the aspects is where dynamic queries. So if you remember what I said earlier about how great this Datomisca library is and that it passes query strings with a macro into a type representation, then you have to know that Scala macros run at compile time. And there is no Scala compiler at runtime usually available. So that means if you don't know the shape or form of your query at compile time, you have a problem. If you have flexible form where a user can sort of build together a complex query, doesn't work as well. But queries in Datomic are just data structures, right? You can just programmatically build them up. But I think this is some of the areas where the library we used didn't offer anything, and we sort of didn't make the effort, because what we did here is we don't build up a data structure. If you look closely, we're concatenating strings. This is probably something you don't show at a presentation normally. It's not very composable, but you know, things happen. Another thing which I want to talk about is this tendency to sort of build something like an ORM on top of Datomic. And ORMs have a sort of a bad reputation, I think, for a reason. But if you think about what they do many, many things, and that's part of the problem. But I want to highlight two things that they do. And one is that they sort of reshape your data, right? You have circles and you want squares. You have relations and you want objects. Or maybe you don't want objects, but that's what you get. And the other thing they do is they force you to access your data in a slightly different way if you use an ORM. Right? Instead of using maybe SQL, if you use a relational database, they force you to go through an interface that's maybe a method or an object, or maybe a DSL, an object-oriented DSL that almost looks like SQL, but has only a fraction of its expressive power. And I think this is where a lot of the criticism comes from. So having said that, I think there are some legitimate concerns in this approach, right? We wanted to have, I think, domain-specific types. We wanted to transform the data that we got from Datomic into something that's called case classes in Scala. And a case class can look like this. So this is a person case class. It has a first name, a last name, an email. If you're into type theory, I think you can call this a Cartesian product of three components. Or in Clojure, there's a thing called def record that's, I think, quite similar. So how did we get that? We got this in this way. And I promise this is the last bit of Scala code I'm going to show. So you see, this is the way we defined our Datomic schema. So for this fictional person case class that I've just shown you. So we define a string attribute for the first name and the last name, and for the email, we want a unique index that you can use the email only once. And then this implicit magic at the bottom of this piece of code. So if you don't know anything about Scala, you can think of it approximately as a sort of Prolog-like logic programming engine inside the Scala compiler that answers questions like, I have a Datomic entity here and I want to use it as a person type. Is there any way, given the implicit conversions in scope, to transform one into the other? And this system, I think, worked really well for us to some extent once we had wrapped our head around it, and that it allowed us to almost transparently use Datomic entities and turn them into person case classes in this example where we need it. But at the same time, I always have this reservation or association of a bucket brigade, right? So you transform from Datomic entities to Scala case classes, and then you transform again maybe into another representation that you use then in your API, maybe JSON. So you write a lot of code about buckets when you're actually interested in the water. But of course, this is just an expression of trade-offs you have to make and that you have to always make. And once we had decided we wanted these idiomatic Scala data structures, I think some things had to go. And the things we lost, of course, is first off laziness. Once you tip one bucket into the other, you materialize the entity. And atomic entities are lazy, but when you materialize them, you load all the attributes that are modeled in this case class, and you're strict suddenly. The other thing we lost is the ability to build, I don't know how to call it, modular entities, if you will. So in Datomic, this is best practice to say an entity is essentially a set of attributes that are grouped together by a common ID, and it's best practice to use the same namespace for the things that appear at the same time. But there's nothing that forces you to do that. You can actually have a nice modularity in how you model your problem by adding attributes as you need them to and from these entities, because as long as they have the same ID, that they're considered an entity. And the way we did this, by tying our code to the data, and if you remember that piece of code I showed you, this is all one namespace where we built this schema up. We lost this capability. And what we also made much harder when doing that is working with sparse data. So Datomic in itself can work great with sparse data. So by that I mean you have entities, some entities that have an email address and some entities that don't have an email address. And an entity is just, as I said, a group of, or a set of attributes bound together by a common ID. So there's nothing that says an entity in Datomic needs to have these and these attributes. And that's sort of similar to what happens in Clojure spec, where you spec on the sort of attribute level, and you don't spec a person. You spec the attributes of a person. Maybe then you do another map spec that defines the keys that you need to have and that are optional. But with our approach, having sparse data became much more complicated, because you have to think now very carefully which of these attributes are always there and which ones are only sometimes there. You might say, well, of course, you have to think about how your data looks like in advance. But I think the problem is more subtle, because over time, the way your data looks might change, right? And when you tie your code the way you did this, you need a very robust migration mechanism if you introduce new required attributes that don't have a default value. Then you have to sort of take care of that situation in the migration mechanism to add these to all the entities that don't have it yet. Otherwise, your code breaks. And there's another implication of that sort of way of doing things, and that is that you limit your ability to time travel at the same time. I just told you earlier how great it is and how nicely that worked. But in combination with this approach, what we of course have is that your code doesn't time travel with you as you go back with the database through time. And so you have to take extra care. If you want to use that sort of time traveling property, you have to build your code in such a way that it's flexible enough to accommodate the absence or presence of certain attributes, let's say. Now, there's more to be said. I could, I think, talk about how we solve the problem that you cannot store large binary objects in Datomic, or we could talk about how we solved issues around ordering things, because what you get back from Datomic is just sets. So when your entities don't have a natural ordering that you can apply afterwards, how do you go about that? We could talk about how great it is to get Emacs out and write a transaction function in Clojure, and how anticlimactic it is then to copy that code into your Scala IDE. But I don't want to do that now. Instead, I sort of want to zoom out a bit from the Datomic Scala picnic and think a bit about the broader implications of using a technology like Datomic. And I think what I've observed is that it has a certain effect on you and your team that sort of goes beyond providing you with a database solution. It has this, what I would call a cross-pollinating effect. Because some of the ideas at its core are so powerful, like, for example, that data is at the center of what you do, of how you solve your problems, that it sort of seeps into other areas of the things you do and influences solutions you find and design decisions you make. And one example I want to give is this. So remember what I said earlier about the application that we were building, about the problem we were solving, right? I said we were doing configuration management. So we were sending chunks of configuration, maybe through a queue, to a remote system where they would be applied. Now, this has nothing to do with Datomic. This is the part of the system where Datomic is not involved. These are legacy systems that are reconfiguring with completely different data stores. But these data stores are not empty, right? There's already data in there. So how does this new data that's coming in relate to the existing data? So you need some sort of mount point. And the way we solve this is this. So you could interpret this chunk of JSON as follows by saying, when this reaches its destination, then have a look for a company called Acme Incorporated. And if you find a unique result for that, then add a new person to that company called Ben Bitdiddle. Now, and this, in retrospect, seems to me awfully similar to what Datomic does with lookup refs, where you want to work with an entity, but you don't know its ID. So what you can do is, instead of using the ID, you use a unique attribute of the entity and its value, and can use it in every place where we would usually use the ID and it's replaced. And that's nothing else what happens here. So we basically replace this inner object, this nested object, with the ID of the company that we don't know because it's somewhere else. So I think the point I'm trying to make here, that you benefit in unexpected ways from using a solution like Datomic, and it sort of has an influence on what you do beyond being a database. But I want to zoom out even more now and come back to the original question. So why is this? If all I said is true about Datomic and the way we adopted it, why is it then still that we can describe it as foreign, or Clojure by association as foreign? And you can look at this problem from many perspectives and angles, I think, but the way I want to look at it now is sort of inspired by a German sociologist called Niklas Luhmann. And he described the whole of society as systems of communication, as recursive, self-referencing, and self-reproducing systems of communication. And that's just an aside. He has a very interesting, if you want to follow up on this, intellectual sort of genealogy that points back to Spencer Brown's laws of form, Alonzo Church, and what was back then called cybernetics research. So, but if you take now his sort of look at things, then what we discover, or what we observe, is that this tendency in our field of software development to introduce more and more distinctions, to break it down in smaller and smaller groups or communities or ecosystems, ecospheres. There are many words for this, and Luhmann would probably call them systems. And there are different kinds of reasons for that. There are economic interests at play here, but also if you look at the media we use to communicate, then they sort of facilitate this process. Just think of Twitter. I think Twitter is somewhat unique and novel in its properties, in that it allows you to have the impression that you're talking to a global audience. But what you're actually doing is you're selecting very carefully who you want to listen to and which parts of which information you want to exclude. So it has this, it reinforces or even creates this effect of sort of breaking the field down into smaller and smaller fields, and almost can create the impression of an alternate reality. Now, of course, this observation is just specialization, what's happening here. We're specializing. There are specialized meetups for Clojure, Scala, I don't know, React.js, conferences like this one, there are mailing lists and other ways and forms. So this is just a field specializing itself. But if you compare this with the Renaissance ideal of the uomo universale, so this person who's master of all disciplines, then we know that we cannot be that kind of person anymore. Not a single scientist today can be the master of all sciences, not even of his own field. You are sort of master of a subset of your field, even as a scientist. And I think the same is more and more true with software development, right? So what does that mean? I think it means that there is this interesting tension between mastering the tools that are close to you, maybe because they solved the problem for you in the past, or because they were familiar to you in the first place, and processing this sort of irritating amount of novelty around you. And of course, learning new things is good fun, right? But it's also expensive. So, and even if an adoption of a technology like Datomic works as smooth as it went for us, I think, and I don't think we hit any major roadblocks despite what I said earlier, then there's still a price to pay, yeah? You have to invest in learning this, in convincing your team members to use it, maybe convincing your boss to use it. So there's no simple answer for this problem, how to deal with that. But I guess what you need is an additional skill. So instead of just mastering your craft, instead of just being the best Clojure developer on the planet, you also need to sort of have a new sort of scientific skill which deals with the complexity of options that you have to choose from. And that skill means looking at those things that are not close to you, that are further away, and pulling them a bit closer to you to have a better look and to decide whether you want to pull them even closer and make them part of what you do. And I think that's all I have, and thanks for your attention.